All right. Hello, senior math. In the past weeks, we've been looking at standard deviation and how to calculate standard deviation. So today we are going to sort of build on top of this a little bit, and we are going to talk about something called Tchebysheff's theorem, which kind of sounds a little funny to say, but we'll talk about this. So last Wednesday, you completed an activity where you looked at two different brands of paint and had the same mean for their data, but completely different variability with the spread of their data. So we had two brands of paint that they had the same mean, their average was the same, but their variability was different. So they had different standard deviations. One was much wider, it had much larger variability. One was much closer, it had a closer range together. So we are going to look at these averages and standard deviations, and we are going to try to talk about something called Tchebysheff's theorem, which can help give us another idea of how these results sort of spill out of this data. All right, so today we're going to look at a theorem that shows where the different percentages of data will fall based off of the standard deviations in the mean. So if we essentially you have a mean, which is always going to be your average in your center, and then we have standard deviations that represent the average distance of each of those points away from the mean. So what is the average distance that each of your points have from the mean? Well, most of your points are going to fall within closer towards that average than they are going to fall away from the average. Most of the points are going to be close to the mean than away from mean. So you're going to have a larger percentage that are close to the mean than you are going to have away from the mean. And so Tchebysheff's theorem helps us it's a theorem that tells us the exact percentage of, or the base percentage or the maximum percentage of points, or sorry, not the maximum, the minimum percentage of points that must fall within certain standard deviations away from our mean. So Tchebysheff's theorem is given a data set, at least 1 minus 1 divided by k squared of the measurements will lie within k standard deviations away from the mean. All right, so this is just a bunch of math mumbo jumbo. Let's try to break this down. So given at least, so that means the minimum amount of data is going to be this formula of measurements will lie within k standard deviations of the mean. So k represents your number of standard deviations, and this formula represents the amount of data that's going to fall within that many standard deviations of the way from the mean. So let's use this and let's try to break this down and figure out what this actually is, what this formula is actually showing us. So if I have k equaling 1, so this means that this would be, wait, I messed up something. I'm sorry, I wrote this down wrong. Give me a minute. Let me pause this. All right, sorry about that. All right, I'm actually going to skip k equals 1 for now because that's like the one example I wasn't supposed to do. So sorry, k equals 2. Sorry, I checked my notes really quick. All right, so let's say we are looking for what percentage of data is going to fall within 2 standard deviations away from our mean. So we're going to say k is 2. So k represents 2 standard deviations. So this formula says we need to do 1 minus 1 divided by 2 squared. And this is going to tell us the percentage of data that falls within our mean. So if we try to simplify this, 1 over 2 squared is like 0.5 squared. So when we square a fraction, we square the top and the bottom. So that's going to be 1 squared essentially divided by 2 squared. Well, what is 1 squared? 1 squared is just 1. So this is just really 1. Or sorry, 1 times 1. 2 squared is 2 times 2, which is just 4. So we are doing 1 minus 1 over 4, which is 3/4. Because 1 is the same as 4 over 4. So 4 over 4 minus 1 over 4 gives us 3/4, which is the same as 75%. So 75% of our data will always be, at least 75% of our data will always be within 2 standard deviations away from our mean. So within 2 average distances away, we should have 75% of our data. We could do this with k equals 3 as well. So that would be 1 minus 1 over 3 squared, which is essentially the same as 1 minus 1 over 3 squared, because 1 squared is 1 squared, which is minus 1 over 9, because 1 squared is 1, 3 squared is 9, which means this would be 9 over 9, so our answer would be 8 over 9, which actually simplifies down to 89%. So 89% of our data is going to be within 2 standard deviations away from, or 3 standard deviations away from our mean. I'm sorry. Now, the reason we can't do 1, the reason Tchebysheff's theorem fails for 1, I forgot about this, is because if I plug 1 in for k, I would have 1 minus 1 over 1 squared. Well, 1 over 1 is just 1. 1 squared is 1, so this is 1 minus 1, which equals 0. So that's saying 0% of our data is within 1 standard deviation away from mean. That doesn't make sense. So 1 fails. But if k is 1, if we're only looking at 1 standard deviation away, through other methods, we are able to determine it's roughly about 68% of your data. It's not perfect, but it's roughly about 68% of your data should be within 1 standard deviation. So I started with a wrong measure, and I completely forgot about that. Sorry. So these are our 3 amounts. We have within 1 standard deviation away from mean, we should have at least 68% of our data. Within 2 standard deviations away from mean, we should have at least 75% of our data. And within at least 3 standard deviations away from mean, we should have 89% of our data. It gets pretty hairy when you start going farther and farther and farther. It gets pretty much all of your data should be within 80. All of your data should be within 4 standard deviations and 5 standard deviations. And at that point, you start getting into more of outliers outside of your data. So let's look at an example of this. Let's look at a picture. So we have this curve here. This curve represents all of the data you have given to you. And so you're going to get a lot of your data. You're going to get more amounts of data closer towards your mean. In this case, your mean is 80. That's the average of your data. You're going to get the most of your points are going to be close to the average, and you're going to get more and more data that's closer to the average, because it's much easier to be closer towards the mean than it is to be farther away from our mean. So if we are talking about standard deviation in Tchebysheff's theorem, so we have standard deviation of 5 with our mean of 80. That means within 1 standard deviation away from our mean, so 1 standard deviation above and 1 standard deviation below our mean, this should represent 68% of our data. So 68% of our data, at least 68% of our data, should fall within 1 standard deviation away. So within that first step away from my mean, all 68% of my data should at least be within here. If I were to go 2 standard deviations away, we said 2 standard deviations would be 75% of my data. So from 70 to 90, this should represent 75% of my data. And this is including that initial 68. So it's really only an extra, let's see, what is that? An extra 7% is really only within these extra 2 pieces is 7%. But 75%, at least 75% of our data. Once again, it's at least. So it's possible for it to be more, but at minimum, 75% of our data needs to be within 2 standard deviations. We could go another set of 5 over. So another set of 5 below, another set of 5 above, because we're just going away from our mean. And that would give us 3 standard deviations. Now, we said 3 standard deviations with 89%. And at that point, we're hardly getting any extra data. Most of our data should already be within 3 standard deviations, but at minimum, 89% would be within 3 standard deviations, if not more. So what we use Tchebysheff's theorem for, it can be helpful for giving us ranges to identify different percentages of our data. So if I want to figure out between what ranges is 68% of my data going to fall, I can use Tchebysheff's theorem to figure out those ranges pretty easily, or 75% or 89%. So let's look at an example of those. So there are 25 measurements of a student test scores. The mean test score is 75, and the standard deviation for the tests are 10. Use Tchebysheff's theorem to describe the percentage of data in each interval. So we are going to look at those 3 different intervals, the 68%, the 75%, and the 89%. And we are going to use Tchebysheff's theorem to figure out what are the ranges that these data should fall within. So 68% was 1 standard deviation. So this means our mean, we only need to go 1 standard deviation above and 1 standard deviation below our mean. Once again, that funny looking U symbol, that's our Greek letter mu, which stands for the mean. And our O with the little line coming off of it, that is sigma, and that stands for our standard deviation. So one standard deviation above and below our mean means we're going to take our mean and we're going to add a standard deviation from it, and we're going to subtract our standard deviation from it, and that's going to give us our two values. So I have a mean of 75 and a standard deviation from 10. So I'm going to do two calculations. I'm going to do 75 plus 10, and I'm going to also do 75 minus 10. I'm going to write this. I'm writing it at the same time just because I'm lazy and I don't want to have to write it twice. But I'm doing two calculations, 75 plus 10 and 75 minus 10. Now 75 plus 10 is going to be 85. 75 minus 10 is 65. So the range of my data for 68% should be within 65 to 85. So I know I'm going to have at least 68% of my test scores are going to fall within 65 to 85 on the test. I can also do 75%. So we know 75% of our data represents two standard deviations away from our mean. So I know my mean plus deviations should be within 75%. So in order to calculate this, I'm just doing 75 plus or minus 2 times 10 because I'm taking two standard deviations. I'm doing that distance twice. So I have to think, what is 75 plus 2 times 10? Well, 2 times 10 is 20. So 75 plus 20 is 95. 75 minus 20 is 55. So 75% of my students are going to score between a 55 to a 95. At least 75% of my students. Once again, it's minimum. And then lastly, 89%. At least 89% of our students should fall between 3 standard deviations away from our mean. So that means it's 75, our mean, plus or minus 3 times 10. 3 times our standard deviation. So 3 times 10 is 30. So I'm doing 75 plus 30, which is all the way at 105. And then 75 minus 30, which is all the way down to 45. Now you're probably thinking, okay, Mr. Jarvis, how can I get 105 on an assessment? Well, once again, these means at minimum 89% of our data has to go within that. So it's possible that the range might exceed far past what the value is possible for. So it's possible that students might not be able to get 105, but we know within those ranges at least 89% of our data is in there, if not all of it. So it's possible that we don't have students going all the way up to 105. But these are our 3 ranges. So all you have to do is you take your mean, add your standard deviation, and subtract your standard deviation either once, twice, or 3 times with a little bit of multiplication in there. And that's how we can calculate these ranges. So suppose you want to create a picture for relative frequency for a large data set consisting of 1,000 observations from the survey. You know that the mean in the standard deviation of the data set is 36 and 3 respectively. So our mean is 36, our standard deviation is 3. We can use Tchebysheff's theorem to create a relative picture and a relative idea of what these ranges are for the different percentages. So once again, our 3 percentages were 68% for 1 standard deviation, 75% for 2 standard deviations, and 89% for 3 standard deviations. So if I want to figure out what is my range for 68%, I know I'm doing my mean plus and minus 1 standard deviation. So that's going to be my mean of 36 plus and minus 1 times 3. Well, 1 times 3 is just 3. So 36 plus 3 is 39. 36 minus 3 is 33. So from 33 to 39, I know I have 68% of my data. Same idea for 75. I'm doing my mean plus or minus 2 standard deviations now. I'm going 2 standard deviations away from my mean. So it's going to be 36 plus or minus 2 times 3 because I'm doing 2 standard deviations. Well, 2 times 3 is 6. So 36 plus 6 is 42. 36 minus 6 is 30. So between 30 to 42 is 2 standard deviations away. Once again, this includes my 68% that I already did because 33 to 39 fall within 30 to 42. And then lastly, we know at 89% of our data falls within 3 standard deviations. So we need to do 36 plus or minus 3 times 3. Well, 3 times 3 is 9. So 36 plus 9 is 45. 36 minus 9 is 27. So we know from 27 to 45, there is at least 89% of our data, if not more, of our data is within those two ranges. And that is pretty much how we use Tchebysheff's theorem. But sometimes we can go backwards. So let's say 24 students' heights are measured in inches. The mean of the data set is 65 inches, and the standard deviation of the data is 2.5 inches. What interval would 75% of the data lie within? What about 89% of the data? So when it asks what interval would 75% of the data lie within, it's telling me, okay, I'm looking for where is my 75 percentage. Well, I know 75% is 2 standard deviations. So that means it's my mean plus or minus 2 standard deviations. Well, if my mean is 67 inches and my standard deviation is 2.5 inches, that means I would have 67 plus 2 times 2.5. Well, 2 times 2.5 is 5, so it's 67 plus 5, 67 minus 5. So 67 plus 5 is 73. 67 minus 5 is 62. So between 62 to 73 should at least 75% of my students' heights in inches should fall between. And once again, we could do the exact same thing for 89, but instead we know 89 is 3 standard deviations. So we just do our mean plus or minus 3 standard deviations, and then we could easily calculate that as well. Let's look at one last question. So our last question, the length and time required for a driver to respond to a particular emergency situation was recorded in 10 measurements. So the time in seconds were 0.5, 0.8, 1.1, 0.7, 0.6, 0.9, 0.7, 0.8, 0.7, and 0.8. Find the mean of the standard deviation and then use Tchebysheff's theorem to find the percentage in data in each interval. So in this problem, they're actually asking us to do 2 steps. The first thing they're asking us is they're saying, hey, you need to figure out what is the mean and standard deviation of this data set, and then you need to use it to calculate Tchebysheff's. So luckily for us, we can easily calculate mean and standard deviation using our Desmos calculator. As an example, why don't we just do this one to show it? So all we need to do is we need to pull up Desmos. And then from there, we can type it in to our data. So we can do mean, put a parenthesis, and we have 0.5, 0.8. We have 0.5, comma, 0.8, comma, 1.1, comma, 0.7, 0.6, 0.9, 0.7, comma, 0.7, comma, 0.6, comma, 0.9, and then 0.7, 0.8, 0.7, 0.8. So 2 more. 0.7, comma, 0.8, comma. All right, so that's our data. So our mean, where did we mess up? Oh, I didn't put a comma in between these two. There we go. All right, so that's our data. So our mean is 7.6. So we know our mean is 7.6. We can also do standard deviation P, put our parentheses. I can just copy this whole list up here and paste this down here below. And I get a standard deviation of 0.15, 0.16. So my mean is 7.6. My standard deviation is 1.16. So I can use that to solve for my solution. So we had a mean of 0.76, a standard deviation of 0.16. And so using Tchebysheff's theorem to find our different percentages, let's just do the first one, 68%. I assume you would be able to get the other ones. So 68% we know is our mean plus or minus 1 standard deviation. So we know our mean is 0.76. 1 standard deviation means we're only adding 1 times 0.6, which is just 0.6. So 0.76 plus 0.16 would be 0.92. 0.76 minus 0.16 is 0.60. So from 6.6 seconds to 0.9.2 seconds is our 68% of our responders are going to be able to respond to whatever emergency situation in their vehicles within that amount of time. And that is where we're going to end our standard deviations lesson for today. And you'll have a little bit of practice of this and then an exit slip to end out the period. Let me know if you have any questions. Have a great